7.5, Conic Sections. What we're going to be looking at in this last section of this chapter really fits more along the lines of analytic geometry. Whenever you think about what is called a conic section, what you need to have in your head is something like this. This is made up of two cones, each called a nap. It has two naps on our double cone here. And if you sliced through this cone at different angles, okay, with a plane, here if you come at it from this angle, you end up with something that doesn't look quite like a circle, but it's actually a parabola. If you come at it with no angle there, we might get a circle. If it's intersecting twice here, but it's slanted, we might get an ellipse. And then if you sliced it along the side where you actually intersect both cones, then you might have a hyperbola. So these functions are going to be defined in terms of a couple of things. One is called the Directrix, and another is called the Focus. So let's start with the parabola and get a grasp on where we are. A parabola is the set of all points whose distance from a fixed point, called the focus, is equal to the distance from a fixed line, called the directrix. The point halfway between the focus and the directrix is called the vertex of the parabola. So you're probably quite familiar with this, but the equation for a parabola is going to be y equals 1 over 4p times x minus h squared plus k. Our vertex is that point hk, which we have right here, given from the form there. Now, the number p, the value for p, tells us how far away we are from our focus. That's what that is. Okay, that value p is telling us how far we are away from our focus, and also how far our vertex is from our directrix. Now, this is the standard form of a parabola, but this equation produces a parabola facing up or down, depending on the value of p. If p is negative, okay, then we have facing down. If p is positive, then we are facing up. But more generally, we can say that it might face left or right if we have x equals y minus h squared plus k, something like that. So here are our four cases when it comes to that. And these pictures are straight out of OpenStax Calculus Volume 2, so feel free to check them out there if these are not clear enough for your taste. A parabola facing up, and we have our focus here. Well, our vertex is hk. Well, h and then k plus p, there's our focus. That point is always just inside the curvature of our parabola. The directrix is then a line here. And if you notice, the distance, it is k minus p, and then k plus p for the focus. Those are always in opposite directions going the same distance. And how we defined this is that the points on our parabola are the same distance from the focus as they are the directrix. So this point right here, the distance here and the distance here are going to be identical. Okay, that's how they're defined. So there's facing up, facing down. Those are fairly self-explanatory. Left and right are the same idea, except instead of adding to the k value from our vertex, we're actually adding to our h value so that we go left or right, respectively. And there's the general formula for a parabola facing left or right. To account for all possible cases, a parabola is in this form: ax squared plus bx plus cy plus d, or, switching those out, ay squared plus bx plus cy plus d equals 0. So we are going to take this equation here, x squared minus 4x minus 8y plus 12 equals 0. We want to put it into standard form and then graph the parabola. Now, one thing you should notice pretty quickly is because I have an x squared term, that's going to be an opening up or down versus a left or right. If it was a y squared, that would tell me it's opening left or right. So to put this in standard form, first, x squared minus 4x plus, I'm going to complete the square here, because I need an x minus h squared. All right, minus 8y plus 12 equals 0. To complete the square there, That would be a plus 4, so we'll add 4 to both sides. So this will be x minus 2 squared minus 8y plus 12 equals 4. Now we want to get y alone, so we'll subtract 12. That will be a negative 8. 12. So that'll be a negative 8. And I'm going to go ahead and subtract this term over as well. Let's make that minus 8. That's negative x minus 2 squared equals negative 8y. Dividing by negative 8, we get y equals negative 1/8 x minus 2 squared plus 1. So my vertex is at the point 2, 1. Right, now my p-value, I want to go ahead and note that 1 over 4p is equal to negative 1 over 8, which makes our p-value equal to 2. Which means my distance to the focus is 2, and since it is opening up or down, in this case it's actually opening down, we'll have a point going 2 in either direction, or actually p is negative 2, which is why we have opening down there. Alright, so it's going to be facing down, we have our vertex, negative 1/8, and I don't really want to guess at this, but I can go ahead and tell you my directrix is this line right here. My directrix is y equals negative 1. Okay, based off our p-value and where my focus is. Alright, now let's see, negative... Oh, that's actually a positive 1/8. That's why this is not looking right. Positive 1/8. Okay, 2, 1. My p-value is positive. Okay. P-value is positive 2, so that all lines up. Okay, my graph matches. Alright, now we can get some other points. These parabolas are always symmetric about their vertex, which we have already labeled. So let's see. 0, 4, 0, 3 over 2. So we'd have a point like right in here. So it should be of this form right here. It will look something like that. The 1/8 value actually makes it wider in this case. Well, it always does. If it's bigger than 1, it will make it narrower or shrink. Horizontal shrink. Next, we'll look at an ellipse. Okay, an ellipse is the set of all points for which the sum of the distances between two fixed points is a constant. So these 2 points that are already labeled here, this point A, if you add the distance from here to that point F, our focus, and here we have another focus, if you add the 2 distances together, you get some fixed constant. Okay. Same thing with this point right here. If you add up the distance between that point to each of those foci, add those together, it's going to be some constant that's fixed. So in this case right here, the major axis is the x-axis, okay, because it is longer than it is tall. So this is the minor axis, this is the major axis. You can obviously have that happen the other way, where the major axis is vertical and the minor axis is horizontal. You can have that happen as well. Okay, so let's go ahead and look at the standard form of an ellipse. Consider the ellipse with the center HK, horizontal major axis with length of 2a, and a vertical minor axis with length of 2b. Then the equation of the ellipse in standard form is x minus h squared divided by a squared plus y minus k squared over b squared equals 1. So this value, a, is the length, or 2a is the length of the major axis. Well, if you notice, this value here, this distance from here to here, It's labeled down here, actually. That is A. That's the distance there. Therefore, the length is 2A. Oop. Stop. Measure the whole thing. So 2A is the length of the horizontal axis. That's why it has the 2A there. Now, you can tell which one is the major or the minor, which direction it goes, because the A, or the A squared, if that's bigger, then that'll mean a horizontal major axis. That's in the x direction, with a length of 2 times whatever that A value is. Okay, if the B squared, if what's next to the y minus k squared, if that is larger, then that will be, we will have a vertical major axis. So if it's going in the opposite direction, effectively those two are opposites. So whichever one of those is bigger is our major axis, and so I use that to kind of inform our decisions going from there. And we can use those equations there to find the foci and to find the directrices. So put the equation 9x squared plus 4y squared minus 36x plus 24y plus 36 equals 0 into standard form, and then graph the ellipse. So what we did with the parabola, we have to complete the square. We're going to do that twice. All right, so this will be 9x squared minus 36x plus something. I'd like to know what that is. Plus 4y squared plus 24y plus something equals negative 36. I'm just going to go ahead and move that over. Plus something. All right, now, I'm going to need to have just an x minus h or a y minus k, so I'm going to go ahead and factor this out. So x squared minus 4x plus something plus 4, y squared plus 6y plus blank equals negative 36 plus that something. Okay, so if I complete each of these squares, that is going to be a plus 4, which means I really need to have a 36 here. Okay, 9 times that value. And then down here, that would make a plus 9, which means I really need to have a 36 there as well. So I'm going to add 72 to both sides there. So this will be 9, and then that is an x minus 2 squared, plus 4, y plus 3 squared, equals 36. Now, this needs to be equal to 1, so we're going to divide by 36. So I have x minus 2 squared over 4 plus y plus 3 squared over 9 equals 1. All right, so this ellipse is centered at the point 2, negative 3. 2, negative 3. All right. Now, my major axis is a value of 3 in the vertical direction. So my endpoints are here and here of my ellipse. My minor axis is 2. So going horizontally 2 in either direction, that gives me my ellipse. All right. Now, I really would like to know where the foci are. Okay. Well, the foci are going to be on either end. Now, what we need to do is find, in this case, our major axis is vertical, so we're looking at that second equation right there to find the foci. H, comma, k, plus or minus c. Now, we could find a value of c. C squared equals a squared minus b squared. Well, our a squared is 9. Let's go ahead and write that. 3 squared minus b squared Oh, switch that. No. Yeah, that should be good. 9 minus 4. Okay, this is going to tell us the direction we need to go. So, oh, that's 2. That's why that looks strange. Okay, there we go. 9 minus 4, so that's 5. So our C is the square root of 5. So if we start at our vertex and go towards along the major axis, square root of 5, which is 2 point some odd, our foci are going to be right around there. Again, starting at our vertex, going opposite direction, square root of 5. Next, we'll look at a hyperbola. The hyperbola is sort of the odd cousin, the opposite in some sense, of the ellipse, because this is the set of all points where the difference between the distances from the two fixed points is constant. Instead of the sum of them, like it was with the ellipse, it's the difference. The difference. So here's what they look like in general. Now, we have a couple of similarities. One is that we have a minor and a major axis. Okay, we have two vertices, like we had in our parabola, and the distances here are determined by values in our equation. We can find our center from our equation, just like we did previously. Now, these actually have two asymptotes. If you notice, these two asymptotes actually are diagonals of this box, per se, that is formed by the vertex and the center. Okay, a rectangular like I said, box in there that sort of is mapped around that. So when we go to graph things, we might actually sketch that box just so we can have a good idea. All right, so the equation of the parabola in standard form is x minus h squared over a squared minus, that's the big difference here, y minus k squared over b squared equals 1. And this is where we have a horizontal major axis and a vertical minor axis. If it's the other way, then we don't switch these two because of the subtraction. We switch these two right here. But the idea is the same, that the major axis is going to be the bigger constant, and then you can tell if it's minor or major from whether it's the x or the y factor there. And we'll come back to these formulas in a second as we need them. Put the equation 9x squared minus 16y squared plus 36x plus 32y minus 124 equals 0 into standard form and graph the resulting hyperbola. And then we'll want to find the asymptotes. All right. We're going to complete the square again. So 9x squared plus 36x plus something yet to be determined minus 16y squared plus 32y minus 124. Actually, let's move the 124 to the other side. All right, now I'm going to also, like I did previously, factor out a 9. X squared plus 4x plus blank minus 16, y squared minus 2y plus something equals 124 plus something there. All right, completing the square in the first box should be a plus 4. So that means I actually want a plus 36 up here, since I did just divide it by 9, going down, and multiply by 9 going up. Down here, that'll be a plus 1, which means we have a minus 16 we included in there, which means in total we're adding 20 to both sides. All right, now factoring that, we have x plus 2 squared minus 16, that'll be y minus 1 squared equals 144. Dividing both sides by 144. All right, that would be x plus 2 squared over 16 minus y minus 1 squared over 9 equals 1. Okay. So I can tell that my center is -2, 1. There's my center. Now, my vertices, well, my major axis is the x-axis, and I'm going 4 in either direction. Okay, so there's my vertex, go 4 to the left and the right. My minor axis, major, is the x-axis. Just label that. Whoa. Alright, my major and my minor. Alright, so my value of A is 4, my value of B is 3. My value of H is -2, my value of K is 1, that's from my center. Alright, now the minor axis is going 3 in either direction, so 1, 2, 3. Alright, so I'm going to go ahead and sketch this box, really, because I want you to see where I'm going with this. Alright, so I have my 2 vertices, and if I were to draw the diagonals of this box, that rectangle, if I were to draw these, those are my 2 asymptotes. My function is going to go through the vertex and approach those 2 asymptotes. And that is what it's going to look like. Now, I should probably emphasize here that these asymptotes are not generally, I'm going to make them dashed, they're generally not drawn as solid lines because, well, we get close to those, they're not actually part of our graph itself. Now the equations of those are y equals plus or minus, or k plus or minus, b over a times x minus h, because we have a major axis that is horizontal. All right, so we have 1 plus or minus b divided by a, that'll be 3/4 x minus h, so that's plus 2. And there are 2 oblique asymptotes for this. Now, an alternative way to describe these conic sections involves the directrix, the foci, and a new property we're going to talk about called eccentricity. So the value of the eccentricity can actually uniquely tell us whether we have a parabola, a circle, an ellipse, or a hyperbola. The eccentricity can tell you that. So by definition, eccentricity is the distance from any point on the conic section to its focus divided by the perpendicular distance from that point to the nearest directrix. Okay, so it's a ratio of the distance to the focus, okay, and divided that by the distance to the nearest directrix. So if eccentricity equals 1, it is a parabola. If it's less than 1, it's an ellipse. If it's greater than 1, it's a hyperbola. Now the eccentricity of a circle is 0 because, well, you know, the focus, well, there isn't a focus there, is there? If it is, it's the center, which means it's going to be 0. So we'd have 0 divided by 1. Okay, so we have 0. So the directrix of a conic section is the line that, together with the point known as the focus, serves to define the conic section. Alright, so the equation to find the eccentricity in general is c divided by a. C is our distance to the focus, and a is the distance to the directrix, in some sense. Right, so let's determine the eccentricity of this ellipse. Now I can tell you what the minor axis is. The minor axis is horizontal, and the major axis is vertical on this one because of the positions there. Okay, 25 is larger. That is in the vertical direction. So my A value is 5 and my B value is 4. Now with an ellipse, this is of the right form, but with an ellipse, we can find c squared, or c, by saying c squared equals a squared minus b squared. So that would be 25, let's write this as 5 squared minus 4 squared, which would be 25 minus 16, which is 9. So c is 3. So the eccentricity is c divided by a, 3 divided by 5, which is 0.6. Certainly that is less than 1. This is, in fact, an ellipse. We already knew that to begin with. But we can use that fact. And a similar thing would happen for any of these other, once you're given the equation for either the parabola, the ellipse, or the hyperbola. All right, there is another parameter we can discuss, though, okay, called the focal parameter. So that we can actually use this to write our equations in polar form. Okay, we are going to come back to polar coordinates. So here's how we find the focal parameter for any of our conics. Okay, for an ellipse, okay, it is a squared minus c squared divided by c. For a parabola, it's 2a. That's actually where it comes from in the quadratic formula. These things are all related. The hyperbola is c squared minus a squared divided by c. Okay, now we can find that parameter just using a formula if we have an equation. So now we want to use that p and that e value, the eccentricity and the focal parameter, okay, to find the equation in polar form. So the polar equation of a conic section with a focal parameter of p is actually a function of its eccentricity. Okay, it's either r equals e times p divided by 1 plus or minus e cosine theta, or r equals e times p divided by 1 plus or minus e sine theta. Okay. If it involves a cosine, that means the major axis is horizontal. Remember, our cosine is x equals r cosine theta from before, while the equation involving sine theta means the major axis is vertical. Again, you can think of sine values as y values. If both sine and cosine occur, then our axes are actually rotated. Now, they don't tell us the center here, so we'll have to graph to find that. All right, so identify and create the graph of a conic section described by this equation. So first off, the major axis is horizontal here. All right, and I know that EP, eccentricity times the focal parameter, is 3 because of our numerator. And I know that my eccentricity is 2 because of what's in the denominator. Putting those two together means that my p is 3 over 2. My focal parameter is 3/2. And because my eccentricity is greater than 1, this is a hyperbola. All right, so I can tell you that. It's a hyperbola, and my focal parameter is 3 over 2. So let's look at a graph and table for this function. All right, so here's my table. My theta is at theta equal to 0. My radius is 1. At pi over 4, my radius is 1.24. Let's put it right there. Okay. Pi over 2, I have a radius of 3. And 3 pi over 4, my radius is -7. Which means it's going to be way out here. Okay. At pi, my radius is -3. At 5 pi over 4, my radius is -7. Which means it's off in that direction. 3 pi over 2, my radius is 3. And 7 pi over 4, a radius of 1.2. Now you probably can't see this very well, but what happens here, our center Our center appears to be this point right here. Okay, where r equals 2. And it looks like this. We do, in fact, have a hyperbola. All right. Last thing we're going to look at is the general equations of degree 2. So if you have a function given, or an equation given in this form, ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Okay, that takes into account everything. The graph of this equation is a conic section. If b is not 0, then the coordinate axes are rotated in some way. To identify it, we use the discriminant of a conic section, 4ac minus b squared. Or alternatively, you can use b squared minus 4ac. Just changes the inequality symbol. So if 4ac minus b squared is greater than 0, then it's an ellipse. If 4ac minus b squared equals 0, then it's a parabola. If 4ac minus b squared is less than 0, then it's a hyperbola. All right. Now, as far as the rotations go, here are the equations to give us our new coordinates, okay, based on an angle of rotation theta. So there's a formula that is cotangent theta equals a minus c over b. Okay, and that is based off our general formula. All right, so let's just go straight into and apply these. The procedure for graphing it is the following. Identify the conic section using the discriminant. All right, using one of those two, just don't get the signs mixed up there. Determine theta using our cotangent 2 theta equals a minus c over b. Calculate our new coordinates and then rewrite the equation, and then we can graph it based on our rotation that we found, the angle theta we have. All right, here it is. There's our general form. So identify the conic and calculate the angle of rotation described by this equation. All right, well, first we have a equals 13, b equals negative 6 root 3. I'm going to write these in order. C is 7. D is actually 0. There is no x term. And E is also 0. There's no y term. And F is negative 256. Okay. 4ac minus b squared. If we calculate that, that is 413 times 7 minus b squared, negative 6 root 3 squared. That is equal to 256, which is greater than 0. That tells us we have an ellipse. So we are dealing with a rotated ellipse. Now, how much is rotated? Rotated, that depends. All right, so let's find our angle of rotation. Cotangent 2 theta equals a minus c over b. So that is 13 minus 7 over negative 6 root 3, which is going to simplify to be negative 1 over root 3. All right. Which is equal to negative root 3 over 3. Okay, now that's cotangent, so that implies that 2 theta is 2 pi over 3, and that theta is pi over 3. So we have a rotation of pi thirds, or 60 degrees. Now let's use our values of a, b, and c to calculate the new coordinates. All right, and now that we have pi thirds there, we'll fill in this equation. Cosine squared of pi over 3 plus b, that's negative 6 root 3, times cosine of pi over 3 plus 7 sine squared of pi over 3, which which is equal to 4. Right, so our A value, our new A value in the rotated scheme is 4. B prime, okay, is just equal to 0. And that was based off of our equation. Okay, so it equals 0. All right, easy enough. Our C prime is our A value, that is 13 sine squared pi thirds minus B, so minus our negative 6 root 3. Okay, sine of pi over 3 times cosine of pi over 3 plus our C value of 7 cosine squared pi over 3 okay, which is a total of 16. So our new C value is 16. Our D prime is going to be D, and our value of D was 0. Cosine theta, doesn't actually matter what theta is in this case. Our value of E was also 0. So our D prime is 0. For the exact same reason, E prime is 0 because our D and E values are 0. And F prime is going to be equal to F, which is negative 256. This brings our new equation to 4x squared plus 16y squared minus 256 equals 0. If we rearrange this, add 256 to both sides, and then divide by 256, we get x squared over 64 plus y squared over 16 equals 1. And this is rotated by pi over 3. So our center is 0, 0, a major axis of 8, but it's rotated pi over 3. So it's going to go in this direction, 8, in this direction, 8, and then 4 going in this direction, 4 going in this direction, and we have our ellipse. Roughly. Okay, that brings us to the end of this section and also to the end of this chapter. Be sure that you understand what's going on here. So all of this stuff is really building. We started right with some geometry, the focal parameter, the eccentricity, all these different ways to define what these conic sections are, but we want to end up in polar coordinates. That's kind of how these tie together, and parametric equations lead into that. This is all to prepare you for what might come next. That's the end of Chapter 7.